Introduction to sequential circuits. Sequential circuits are the digital circuits whose output depends on present and previous history stored in flip-flops. So these circuits have memory. Unlike combinational circuits, there are two types of sequential circuits. Synchronic circuits, a compressive guideline to design finite states of machines and detect specific patterns and in digital streams. Introduction to sequential circuits. Sequential circuits are digital systems whose output depends on both current inputs and previous states, unlike combinational circuits that respond instantly to inputs, and sequential circuits have memory. They remember past information through storage elements called as flip-flops. Sequential circuits are clock circuits where all state changes over a clock pulse edges ensure the predictable timing and coordination between components. Since states change of immediately when input changes, design in complex and time may vary. Design in complex and time varying may vary. In this seminar, we focus on semi-synchronous circuits. What is sequence detection? The sequence detection is a digital circuit that monitors a stream of bits and gives a high output when a specific pattern is detected. Example 1011, 110 and 101. This circuit is widely used in digital communication and data frames information and error detection, correction, and recognition. Asynchronous circuits state change over immediately when input change without signal more complex to design analyze. Key components are flip-flop provide memory, combinational logic process data, synchronizing all operations together. These elements enable the circuit to track sequential design based on the historical pattern. What is the sequence detector? A sequence detector is a specified sequential circuit that continuously monitor an input stream and produce a high output signal when a predict pattern is recognized. These circuits are fundamental in digital communication system and decoding errors detection product signal process applications and code definition. The detector sends incoming bits on at a time, maintaining state of information about how many consecutive bits of tracked sequence have been received. When the complete pattern is defined, the output is indicated successful detection. The real world application, digital communication pack headers and data frames, some synchronous error detection, core correction, and protocol recognition in networks. Overlapping versus non-overlapping detection. The fundamental design choose in sequential detection in whether to allow bits from one detected sequence to reduce the start to error. Overlapping versus non-overlapping detection. The fundamental design choose in sequence detection is whether to allow bits from one bit detection sequence to re- reuse start of the next detection cycle. This decision is significantly impacts the circuit complexity, speed, and resources and utilization. Overlapping detector allows bits to share between consecutive detection. After finding the target sequence, the circuit immediately begins checking for next occurrence, reusing the tail bits if they matches the pattern begins. Example, detecting 101 in stream 10101 produces two outputs. Overlapping detection uses the middle bits. Non-overlapping detector. After detecting the sequence, the circuit resets it and begins fresh with next input bit. Now bits are reused between consecutive detection, some simplifying state transition, but missing potential overlapping patterns. Example, some stream 10101 produces only one output. The second pattern after the first complex. Design methodology, step-by-step flow. Designing a sequence detector requires a symmetric approach that translates the desired pattern into a state machine. The implement is using digital logic. Each step builds up the previous, creating a complete blueprint to hardware implement that define target sequence, especially the exact pattern to detect such as 1011 and determine of overlap is required for your application. And a design state diagram create state in and process toward the sequential compilation with transmissions based on input bits and output generation rules. Construct a state table. Documents all state transmission showing present state input, next state and output for every assign a binary codes and map each state to unique binary value that will be stored in flip-flops. Select a flip-flop type. Choose between D, J, K or T flip-flops based on circuit requirements and managing components and count and complements. And drive logical equations and determine execution equations for flip-flop and output equations using Boolean algebra. Implement the circuit, draw the complement logical diagram using and or not gates, combining with select flip-flops. Verify with the timing analysis and simulate the circuit with the test sequences to confirm correct detection under various conditions. Then detecting 101 with overlapping. Let's design detector for the sequence of 1011 that allows overlapping well process through each state as matching bits array with the circuit remaining partial matches to over detection. State definition in one open and you open and transmission and transition connection and entry action. Yes, one is the first step is first one detected. Second, 10 is detected. 101 is detected. 1011 detect output is 1. After detecting 101 at this step 4, circuit is transmitted to S1 reviewing the final one to allow the overlapping detection. Next sequence overlapping transition able to circuits to detect multiple instances efficiently. The final one or 101 becomes the first one of the next potential sequences, reduce the number of input bits and between the detection. Detecting 101 without overlapping. For a non-overlapping detection, the circuit must be reset and the initial sets immediately after successful detection and preventing any bit residues. And this is simplified the state diagram but may miss pattern that span continuously sequences state definition. Step one is initial state and detection begins here. First one is received. First one is state definition. And first one is received and 101 pattern verified and 101 pattern is verified. 101 complete and output is one returns to S4. Design advantages and non-overlapping design is often simpler to implement with fewer state transmission all over power consumption and straightforward state. Much logic and choose this approach when the pattern is redetection must be truly independent. State table and binary set as assignment. The state table formally documents every transmission detector. Each row specify what happened as a present state and input and determining the next state. Instead of and output and binary assignment map states flip-flop values that will be stored as them present input and next state and binary output. Binary assignment as the output becomes one only when complete detection state is S3 input 0 0 0 0 1 0 0 1 0 0 1. S3 is 1, S4 is 11. Implementing with the D flip-flops and logical gates. With the state table complete, we derive a Boolean expression for each flip-flop input and output. These equations are defined exactly how gates should be connected to flip-flops and to create the desired state transmission equation using closed map stable and x1 plus x2 wherever x is input and s1 s2 represents state combination. This equation directly mapped to and or logic gates and feeding and flip-flop d inputs and output equations such as x to s and output equations one only when input is 1 and state represents 101 begin detection. This realization with a single AND gate and checking their conditions simultaneously ensuring output activates previously when the complete pattern arrives. Timing diagram on circuits verification. The time diagram usually confirms and correct detector operations by showing input bits and clock pulse and stage transmissions and output signals of overtime. This essential for verifying that the circuits detects and sequences correctly and the timing meets hardware verification process. Apply now the test the sequences to circuits and track the state of change at each clock edge and confirm output pulse appears exactly when the pattern completes and check timing meets stop and hold time requirements and simulation corner causes and unexpected inputs. Implementation of outputs on hardware FPGA and or CPLD or rapid protection. This is all about the sequences of